Hey, welcome back to Math with Patrick and Quill. Today is December 15th, and we're solving problem 349 from the Daily Epsilon calendar. And you might notice that I'm starting off this video a bit differently because I'm already here on GeoGebra. When I was taking a look at this problem, I needed some help. I wasn't really quite sure what was fixed in this diagram or what could be flexible. And so I created this diagram in GeoGebra to help me out. The idea here is that in the bottom right corner, we have a square. And so I created a regular polygon here in GeoGebra. And so if I take this vertex and move it, I'm fixing this as a square or a regular four-sided polygon. And in the problem, it says that it's at 6, and so that's why I'm fixing the sides at 6. I'm also noticing on the left, we have another square. This one, I am varying up and down like this, just because it looks like that point D in the diagram, which corresponds to my point C here in GeoGebra. This one seems like it is collinear with, well, A and E in my diagram. And we also have another square here. This one is formed by G and E in GeoGebra. And this square kind of changes shape based on how I might change this point C. And then lastly, we have this big square right here. And hopefully HK is going to be, or the segment length there, is going to be 15 to match today's date. And I don't really recognize those chevron tick marks there. Normally you would use those chevrons to say that things are parallel, but then those chevrons should point in the same direction. So I think they're using them as quadruple tick marks, just to show that this indeed is a square. All the side lengths should be the same length. This is a right angle in the top right corner. And if I can interpret this as a square, I actually don't need to worry about it. I could just trash that. Because if it's a square, HD in my diagram, or AB in the picture in the calendar, should be also 15. So if I can prove that this length is 15, then I'm done. And the one thing that I haven't considered yet is that D is the centroid of ABC. The centroid of a triangle is essentially the balancing point. And we can find it as long as we draw 2 or all 3 of the medians. And to find the medians, let me actually do this in GeoGebra. I could find the midpoint kind of tool here. And if I attach a segment from a midpoint to the opposite vertex or opposite corner, then I'll be dividing the triangle in half. And somewhere along this line is going to be my midpoint balancing point, or essentially this centroid, to use the vocabulary word. So I could do this again. Let's get that midpoint, pick another segment. Oh, looks like the midpoint here is already on the this kind of vertical axis here. And then I should connect the midpoint to the opposite vertex. And so it looks like this point right here is the centroid. And I guess just for good measure, let me do it for the last one. Let's get the midpoint of the left segment and then connect that midpoint to the opposite vertex. And then yes, indeed, we can see that the centroid is at the intersection of all 3. So really all I would need to do then with GeoGebra is click and drag this point C until it, or D in the calendar picture, until it matches up with the centroid. And as you can see, as we go up, we get closer and closer and closer, and it seems to intersect right around there. Let me zoom in a bit more. Zoom in more, and it intersects exactly at 9. So this is where we should fix that centroid on our diagram. And now that we know that the height of this square should be 9, maybe we can also say that the segment here is 3. However we want to say it, let's use this number and then prove that this long diagonal is indeed 15. Let me redraw this portion of the diagram just so I can zoom in a bit more. So there's C and D. Here is B. We know that this side is 6 now. We know this side is 3 now. Looks like we have a right triangle there, and we have some kind of unknown distance from D to the segment that joins A and B. However, it's not that unknown. We do know that D is the centroid, and the centroid has an interesting feature where this length is always twice that length. The quick proof is if I just draw any normal triangle here, I'm connecting the vertex to the opposite point. That splits the triangle in half. And so overall, I've split the triangle into 6 equal parts because there's half and then another half and then another half. And then if we study, say, this triangle right here, knowing that all 3 triangles have the same area, we can see this triangle here has then twice the area of this one. And if they have the same height, then the bases should be also twice or half of the other one. So this base should be twice the length of this one, and that kind of proved my claim that we have the centroid cutting those medians into a 2/3 part and a 1/3 part. Anyways, that does mean that D to this point right here, the midpoint between A, B, is going to be 1.5. And so overall, we have a triangle, a right triangle, with a 4.5 on one leg and a 6 on the other. Now, I could just do the Pythagorean theorem on this, but I do recognize this as a 3, 4, 5 triangle. So if I look at it like this, if I multiply 3 by 1.5, I get 4.5. If I multiply 4 by 1.5, I get 6. And so if I multiply 5 by that same scale factor, 1.5, I'll get 7.5. So I could have found this distance by doing the Pythagorean theorem, but I'd rather not work with decimals that way. And here, we're essentially done. We know that this point right here is the midpoint between A and B. Let's just pretend A is right here. So overall, we know that the whole length is 15. And then knowing that it's a square, we can use that 15 and say that x is 15 as well. So there's my solution. I used a little bit of help from GeoGebra to understand the geometry of the situation, but we can show that x is 15 for today. So that's all I got. Thanks for watching, and I'll see you tomorrow. Bye.